No, you write everything up.
Oh, the net, I'm sorry, yeah, the net is just what actually is again. Sorry, for some reason, you were saying that, I'm hearing complete.
I know, it's like one grade is like,
Okay.
and look at it and
Good. I will disagree. All right. So, we are making our way through the thermodynamic chapter. What, next week is exam time, yes? Is that what it is? Is it next week? Week out. Week out, okay. No, sorry, I forgot. Sorry. Sorry, the week after. So we'll be working our way through chapter 5. And what we have learned, or what we're starting to learn here in chapter 5, is just about how energy flows into or out of a system or the surroundings or those kind of things. A little bit of bad news. So the recording for Wednesday's lecture got kind of lost, or Wednesday or Mondays, I forget now. I think it was Wednesdays. Got lost because I accidentally recorded in slow-mo.
There's actually a way to get around it.
Yeah, I might need to figure that out, so I might need to help. So as soon as I can figure out how to, not do that, then I'll post it. But I've got like a 6-hour video of me going through in slow motion how to do thermodynamics, and nobody wants to watch that crap, all right?
Are you sure?
Some of us would pay for that.
So my voice already sounds dorky enough as it is, when it's recorded, and then like in slow-mo it's even worse. So as soon as I get that fixed, I'll put it up for you guys. But what we were getting to, or what we were dealing with, is just how to calculate energy, right? And we had gotten to the conclusion, after a lot of blah, 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 that what we really need to pay attention to is Q. Right? Q is what we're going to be calculating when we're dealing with the energy going into or out of a system, right? And Q is equal to the mass times the specific heat times the change in temperature. So we end up with basically a 4-component equation, and so we need to find information about 3 of those to be able to solve for whatever's missing, right? And so this is kind of one of the let's say maybe the trickier questions along the way. And it asks about energy being lost by a metal block, and we have information about where it initially is, and it asks for the final temperature, and it gives the specific heat. And we set up the equation, and the important thing to recognize here is when you guys went through and calculated your energy, that energy is going to be a negative value for the block of metal, right? Because it says that the block of metal loses, so we know that there's going to have to be a negative value, okay? Now, if that metal block loses energy, where does it lose energy to? The universe, right? The surroundings, whatever you want to say, right? Everything else, okay? So we could have asked this question, what is the energy gained by the surroundings from when a metal block loses it, right? And then it would just change our answer to a positive or something like that, right? So that's the same idea here, okay? Now, the reason why I'm emphasizing this again is because I think it's the next problem is we're going to have to play this game of what gains and what loses, right? What's going to be positive and what's going to be negative, okay? Very important to start to pay attention to that, right? So anyway, at the end of the day, what I got for my answer here was T final. Once I solve this out, I got it to be about 19 degrees Celsius, right? 18 point something there, but if we solve for T final here, we should be able to get to about 19 there. Now, let's pause for just a second, okay? Does that answer make sense? Well, my question tells me I start off at 125 degrees Celsius, and I lose energy. Remember, what's energy really a measure of, or how do we measure energy most commonly? Temperature, right? So if I'm losing temperature, my final temperature better be lower than what I started out with, okay? But if you guys forget your negative, right? If you guys forget your negative here, I think you end up with a value of like 300 or something like that, which doesn't make sense. How could you lose energy and increase in temperature, right? So be careful when you guys get to your final answer, just stop and go, right? Does my answer make sense? Okay? So about 19 degrees Celsius is where we end up. Okay? All right. So here's the next wall of text for a question. So I'm going to give you guys a second to kind of look at it, and then I'll point something out for you guys. Yeah. Very active. I got you. All right, so let's pay attention to a couple things here. So this should kind of stick out there, the equilibrium temperature. So this is kind of one of those flags like you guys see with excess reagent or limiting reagent. Anytime I'm asking you guys for a thermal equilibrium type problem, that's a very specific and very common type of problem that's asked, okay? So pay attention to that term equilibrium, especially with the temperature.
So how do we go about finding?
Yep, I'm getting there. Geez, give me a minute. I got a minute. Right? So what does this mean then? So remember, what is equilibrium telling us? We put something hot and we put something cold. And we let them sit together, and eventually they're going to end up at the same temperature. Right? And that's our equilibrium temperature. So we put something hot, it's going to lose energy. We have something cold, and it's going to gain energy. You guys with me on this? What has to be the value of whatever's gained and lost? Whatever is lost has to be gained, and that value has to be the exact same, right? If it loses 1,000 joules, whatever else has to gain 1,000 joules. So if something has minus 1,000 joules and the other thing has plus 1,000 joules. You guys with me on this? Here's what we're talking about. So what are our things that we're mixing here? What are our things that we're mixing here? Well, we have some copper, right? And we have some water, okay? So the Q of the copper, okay, the energy of the copper, the heat of the copper, right, plus the Q of the water equals the Q of the universe, right? That's pretty added up, right? Right? Oop, I should pick a different color there. Let me just pick, don't want you guys to get confused here. Q of the universe. Okay? What's the Q of the universe always going to be equal to? 0. Got it? So Q of the universe is equal to 0. So Q of the copper plus Q of the water has to be equal to 0. You guys with me? So let's read a little bit here. It says that copper at 500 degrees Celsius is plunged into water at 23 degrees Celsius. So what's the hot thing? The copper. The copper is going to lose energy to the water, right? So what's going to be our magnitude for Q for the copper? It's going to be some negative value. Why am I bothering to explain this? Because what we're trying to do here is we're just going to rearrange this equation, okay? And we're going to say Q of the water, the plus Q of the water, right, equals the negative Q of the copper. You guys with me on this? All I did was just take this to the other side there, okay? And I specifically put my plus and minus there to help me out. When I solve these problems, I gotta put the pluses and minuses there. Because that tells me what gains and what loses. The hot thing's gonna lose, the cold thing's going to gain. What's Q equal to? What's the equation for Q? The mass of the water, right? plus the specific heat of water plus the change in temperature of the water, right, is equal to what? The negative of the mass of the copper plus the C of the copper plus the delta T of the copper. You guys with me on this? Q is always equal to MC delta T. Whether it's the water, whether it's copper, whether it's aluminum, whether it's your desk, right? Q is equal to MC delta T. So now what do we have to do? Do we have information about the mass of the water?
Yes.
Yeah. Do we have information about the specific heat of water? Well, you can look it up, right? I'll give you that. I don't know why I left that out of the question. I'll give you that information, don't worry.
Wouldn't
Right?
it be the T equals 23.4 Celsius?
No, the C.
Oh.
Yeah, the specific heat, 4.184, right? Do we have information about the change in temperature of water? Well, we've got the initial, right? Do we have information about the mass of copper? Yep. Do we have information about the specific heat of copper? Yep. Do we have an initial temperature for copper? Yes, we do. Got it? Let's start to plug some things together here. So mass of water, 1 kilogram, so we'll call it 1,000 grams. Specific heat of water, 4.184 joules per gram degree Celsius. Oops, not plus. Oh my gosh, I'm a big dum-dum, excuse me guys, that's not, of course it's not a plus. Times, sorry. Yeah, sorry. Times, T final minus, 505. The mass of.
Why is it 505?
Hmm?
Shouldn't it be 22.4?
Oh, yeah, sorry, looking at the copper, yep. 23.4 there it is. Degrees Celsius, thank you very much. Mass of the copper, 215 grams. Times specific heat, 0.385. And right now it's room, so let's do this. Change in temperature to final minus 505. What do we have to know, or what do we have to recognize about T final? Remember, this is what we were trying to think about at the beginning. Something hot and something cold. After we put them two together and wait a while, T final's gotta be the same for both of them, okay? The T final for the water is gonna be the same as the T final for the copper.
So we just isolate T final?
So now we just have an equation with one variable, okay? So whenever you see the thermal equilibrium problems, okay, T final's gotta be the same is essentially what that translates to. Okay? Yep.
Where did you get the 4.184?
Yeah, so this is a specific heat of water. I just forgot to put it up there for you guys. Yeah, that's my bad. That's always gonna be given information. Yeah. I think it's even on the equation sheet here. No, it's not on it, but I will always give that to you, yeah. Now the tricky part just becomes making sure you solve the equation properly, right? take a mostly inelegant way of getting to the answer. I just start multiplying things together until I get it simplified. Right? It gets the answer done, right? All right, so one last thing to always take a look at here. T final is 32. If we go back to our answer, or excuse me, to our question here real quick, we started at 505 and 23. So our T final always needs to be somewhere in between those two, okay? So if you end up with an answer that's above 505 or below the 23 there, then somewhere we got our pluses or our minuses tripped up. Go back and double check, okay?
Wait, you're saying we end up with a negative answer?
Yeah, you can, yeah. Well, the answer has to be somewhere in between the two positions there, is what it is. In between the two starting values. Sometimes it might be a negative value, right? But that's just because of where we began with. Our answer has to be between 505 and 23.4.
But in this case, you have no cost.
Yeah,
Okay.
yeah. Yeah, if we started out with like negative 200 or something, it might be ending up with a negative value there or something. Yeah. But it still would have to be in between. It would have to be in the range of the max and the min. Good? So the tricky part about these is just setting everything up and making sure that we have the right values plugged in there, okay? Double check yourself and maybe even triple check yourself. All right. So let's talk about something confusing because we haven't done enough of that yet, right? So we'll get to there in just a second. But so this is kind of a summary of what we've been dealing with so far for what it is, right? When heat is added into a system, the Q is positive. We call that an endothermic, okay? Endo just means inside, right? And thermic, we're just referring to temperature, right? So we're energy. So we take some energy in, that's positive. If energy is removed, Q is negative, and it's exothermic, right? Exo just meaning out, okay? So when you see the terminology of an endo or exothermic reaction, we just absorb or release heat is all we're saying with that. The Q is positive or the Q is negative, okay? What's interesting to think about here, or what's something important, is the phase changes of materials, okay? When we boil something, when we turn something from a liquid into a gas, it takes energy. Now I can tell you guys aren't shocked by this, right? Because how do you boil spaghetti water?
Fire.
Yeah, you gotta put heat onto it, right? Water, if you sip water, it's not gonna start to boil by itself, right? It'll still evaporate though, right? That's interesting, right? Because evaporation is taking a liquid into a gas. Is evaporation endothermic then? Yes, it is, right? That's why you guys sweat when you get hot, right? You sweat, you have water on your skin, that evaporates and you feel cooler at the end of the day, right? So the same ideas at work, but we have to kind of maybe approach this in a different perspective then, right? So we'll talk about why water evaporates even if it's at room temperature, okay? We'll talk about that in the second semester, I believe, is what it is, okay? But yeah, everything's in the second semester, right? But if this is endothermic, the reverse of the reaction is exothermic. So all I want to tell you guys is this real quick, okay? If one way absorbs energy, from liquid to gas absorbs, gas from liquid has to be the opposite of this. And that's going to be important when we get to the next big topic, which will be enthalpy and Hess's law, okay? We reverse a reaction, the Q is going to change, okay?